41, and then move into map testing from there. So the second thing that I want to talk about are grade equivalents, okay? And grade equivalents, the first number is the year, and the second number is the month. So 5.6 means the 5th year of school and the 6th month of school. Usually 0, 5.0, or 6.0 here, 0 would represent September, 1 is October, and so on. So November, December, January, February, March, and so on. So March is the 6th month of the school year. Now, if we are looking at the grade equivalent of this particular student in reading, say, hold on here, I can't see my little arrow. Oh well. Well, what this means is that this student did as well on this test as a student would have done if they were in the 5th grade and the 6th month of the school year. And so grade equivalents represent what the median raw score is for each grade. So a 4th grader in May who receives a 41 on her assessment, we'll say, has a grade equivalent of 5.8. What that means is that she did as well on this exam, and it's important that we say this exam, as the average 5th grader who took the test in May of that school year would have done. And I will refer to Popham. He has a nice little graph in the text that you can look at to talk about how this works. But the big things that you have to consider is what this means and what this doesn't mean. So again, this 41 is a grade equivalent of 5.8. In this case, 5th grader, the median raw score is 37. 5.1 means that that's what the median score is for somebody in 5th grade in October. In the 4th grade in May, the median score, again, and the median is just the middle score. It's kind of like the average, but it's not quite like the average. It's just the middle score. We'll leave it at that. Their grade equivalent would be 4.8, and so on. So if somebody in 4th grade, right in October, took this test and got a 41, they would have a grade equivalency of 5.8, meaning that they did as well on this test as the typical 5th grader in the 8th month of the year would have done on this test. So considerations that you have to think of are that the grade equivalent is not an estimate of the grade that the student should be in. It just means they're good at what the test is on. If for example, say that algebra is introduced in 7th grade and you're a 6th grader and you do really well on your test, and your grade equivalency is like 7.8. You haven't had any algebra yet. It doesn't mean that you should skip, 6th grade and move into it in the middle of the year, because the test wasn't about algebra. It was about fractions. And all it means is that you do fractions well. You do fractions better than the average person. It doesn't mean you can do other things. Just like reading comprehension, and say that you're shifting in those early years from like 2nd, 3rd, 4th, and 5th, from decoding being a big thing of what you're teaching, turning the print into words, into actually understanding, which requires vocabulary and it requires prior knowledge, right? And so just because I'm a good reader for a 3rd grade text doesn't mean, and say I have a grade equivalency of 7.5, it just means I read 3rd grade text like a 7th grader, right? It doesn't mean that I can read 7th grade text. Now, likewise, if I'm a 7th grader and I have a grade equivalency score of 5.8, meaning that I did as well on this text as a 5th grader in the 8th month of the year would have done on this text, all that means is that I can't read 7th grade stuff. Doesn't mean I can't read 6th grade stuff. Doesn't mean I can't read 5th grade stuff, right? All it means is what I can do with this text, with the 7th grade text, relative to other 7th graders. The second thing is that you can't expect that all students are going to increase exactly one grade unit every year. Curriculums change, developmental is not linear, it doesn't follow a nice, neat progression, and tests are unreliable. So you may score high one year and you may score a little lower next year. Not that your ability has changed, but because of the reliability of the test, your score might be higher than it should be in one case and lower than it should be in another case. And that accounts for a lot of the differences that we see in the average yearly growth. The second thing is, don't assume that the units are equal at different parts of the scale. So when we're looking at grade equivalency, right, going back to this, if you look at this, right, the same 7-point difference here represents 7 points on the scale, right, 28 to 35, that's 0.7 points different. That same, when I'm looking at, 5.1 to 5.8, that's only a 4-point difference. So a change, getting one more point in the higher range is going to move you farther up than it would in the lower range or in the middle range. And so when we're talking about thinking about how grade equivalencies are expressed across the whole range of test scores, it is not an equal thing, and you have to be careful in interpreting that. Also, don't assume that scores on different tests are compatible. Just because you are at a grade equivalency of 4.5 in the third grade, after your school district has taken the WKCE for 12 years, when you shift to a new test, don't expect your grade equivalency to be the same, because the content will be different, the types of questions will be different, and likely the format of the test will also be different. Finally, don't interpret extreme scores as reliable estimates of students' performance. If you recall from earlier in the year, norm reference tests are designed to have most questions in the middle difficulty range. You have very few questions that are really difficult, and you have very few questions that are really easy. Because of that, we don't have a lot of questions up at the really high end and down at the really low end to tell us with any kind of certainty where gifted students are or where struggling students are. And so when we look at how reliable our tests are for people on the extremes of the ranges, our scores are much less reliable indicators of what their actual ability is. Now, the next thing that we're going to talk about are national stanines down here. And basically what it does is it breaks down the whole range of scores, right, into half standard deviation units. And because it has 9, we have, if we look at this national stanine scale here, right, this is the whole range, goes from 1 to 9. Here's one standard deviation in the middle, half below, half above. One standard deviation here, one standard deviation here, one standard deviation here, one standard deviation here. Okay, so I have 1/2. All right, well, this is really a quarter, I should say, of a standard deviation. Then 0.75, 1.25, 1.75, 2.25 standard deviations below, and 2.25 standard deviations above the mean. And that represents virtually 100% of the entire range. And if we go back to this particular score, this is 1 standard deviation below, 2 standard deviations below, and once you get past 3 standard deviations, there's only about 0.1% of the people below that on the low side, and 0.1% of the people above that on the high side. When you look at how the percentile ranks, which we're going to talk about, break down within it, and this, you can think of this also as having the percentage of people, right? So in the first stanine, I have 4% of the people. In the second, I have 6%. In the third, I have 11%, and so on, until in the middle, I have almost 20% in that fifth stanine. So when I'm looking at these stanine scores, right, most of my, well, not most of my people, 20% of my people are right here. Only 4% are down here, 4% are down here. Stanines are similar to percentile ranks, which we'll talk about in a minute. But if you look at the difference between the stanines and the percentile ranks, these range from 1 to 9, so there's only 1 digit. And these range from 1 to 99, so you have potentially 2 digits. Stanines were invented back in the day when computers were first invented and they didn't have a lot of memory. And writing a stanine score took up half amount of the memory as a percentile rank score did. And so that's why they were invented. That's why they were used. They basically have no value these days, but people still use them and they put them on test scores. And my question would be, why would you look at this when I can look at the national percentile rank itself and make this better decisions? Because I'm getting, if I look at the Stanines for, total score and science score here, this person's at the 46th percentile. This person's or their score here is at the 38th percentile. There's an 8 percentile point difference here, but they're in the same Stanine. Just like for this one, they're 14 percentile points above in language than they are in reading. And yet, that is just the 4th Stanine again, which is kind of ridiculous. And so Stanines aren't that great. They don't give you anything. And so, oh well, they're just a stupid remnant from a bygone era. The next thing is that we want to talk about our national percentile ranks and national percentile ranges. Percentile ranks is the percentage of people who scored at or below your particular score. It does not mean, in this case, that you did better than 16% of the people, because many of those people in that 16% probably had your same score. That's probably the biggest mistake that people make about it. And when we look at like these little graphs that people have, the diamond represents, and let me go back to this one. The diamond represents what your actual percentile score is, right? So this is at the 16th percentile, this is at the 30th, this is at the 66th, and so on. Now, because tests are not 100% reliable, we recognize that, well, yeah, this is where you scored, but you probably aren't really there. Either you guessed right on a couple, you made some silly mistakes, you ran out of time, you were distracted, whatever. Some reasons you did better, some reasons you did worse. Could be the sampling of the test or whatever. And so we're going to introduce this line that represents where your true ability probably lies. And so the difference here is between your true score, and we've talked about this before, which nobody knows, and it's probably on this line, but doesn't have to be on the line. If the line extended across the whole range, well then I would say that it had to be on the line. But a monkey taking this test, who knew how to fill in circles, might get 10 questions right. It doesn't mean that their ability is really at that particular percentile. Their ability probably should be at 0. But we don't know. Likewise, you might have been a genius, but you missed a question and then all your bubbles were off by 1. And even though your true ability is up here, well, I'm going to say based on your test results that it's down here. So what this line represents, and it depends on the test, but in most cases it's either I'm 68% certain that you're within this range, or I'm 95% certain that you're within this range. Based on the test characteristics and things like that, but we don't need to go into all that stuff. So the diamond, again, represents what your score actually was. It's based on your scaled score. Your scaled score is converted into a national percentile rank, and then given the reliability of the test and the reliability of the section of the test, I will create this band saying that your true score is probably somewhere on this band. And, this person here scored just under this kind of proficient range or normal range. And the bar extends well into that range. And so they could be in the range. And I have to accept that when I'm looking at these kinds of test scores. That even though I get these specific results, the truth of the matter is I'm probably close, but the truth of the matter is probably somewhat different. Now, percentile ranks themselves, they're different for every test when we compare them to raw scores. And like if you look across these different parts of a mathematics test, I have concepts of numbers, computation, applications, right? And I have, in this case, 34 questions, 44 questions, 40 questions, and 40 questions. The 50th percentile down here is 19. 50th percentile here is 26. The 50th percentile here is somewhere around 24.5. And the 50th percentile here is somewhere around 27, more than likely. Now, so different raw scores will result in different percentile ranks for different tests. It also depends on who my reference group is, right? When they're taking the test and under what conditions they're taking the tests, because all those things matter. And if I'm at the 82nd percentile as a 5th grader, right, and then I move up into 6th grade that next week, say, and start taking class with the 6th graders, if I take a 6th grade test, my percentile rank will probably go down. Or if we take the same test, say that the school gives the same test to the kids every year, say in middle school or in grades 5 to 8 to look at how they're developing, my percentile rank will be much lower because I'm now be compared to kids who are a year older and have a year more of schooling. So I have to keep that in mind when I'm thinking of percentile ranks. So remember that they're always norms for a particular group. I need norms for any group that I want to compare, and I don't always have them, and that changes in percentile rank are not consistent across the whole range of scores. And so a 10 percentile increase for average scores in the middle of the range is a much smaller raw increase than it is for higher low scores. And going back to this, that idea is reflected in that when I'm at the 50th percentile, if I increase my score by 1 point, I move up, 3 percentile points. If I'm at 18 and I get a 19, right, if I guess right on one more, I go up 5 percentile points. But if I'm at 33 to 34, I don't change my percentile rank at all, right? It's just the same thing over and over again. Now this is the end of part 1. I'll be right back for part 2.